All right, so for the last section that we're going to have in Unit 4 is working with complex numbers. Now we're going to break this down by, in this video, just learning what a complex number is and doing basic operations with it. And then tomorrow, we're going to kind of work in how this works with the quadratic formula and just quadratics overall. So you don't need to write anything down here, but where we have left off in this unit is we're finding zeros or we're solving for quadratic equations, but sometimes you have a situation like this, where our parabola does not cross the x-axis, so we would say that that has no real solutions. And another way that we saw that algebraically is when we would try to solve using the quadratic formula, we'd end up getting a square root of a negative number as the discriminant, and as you've probably tried in your calculator, if I try to take the square root of a negative number, it also tells me no real solutions. So that leads into another set of numbers entirely called the imaginary number system or complex number system. So if I don't have any real solutions, I could have imaginary solutions, or in other words, a complex solution. So here, I'll start writing stuff down. The imaginary unit I is the complex number whose square is -1. So the whole complex number system is based off of negative square roots, essentially. The name of the game here is that I squared is -1 and I is equal to the square root of -1. I would highlight this, star this, just wherever you can remember this, that is going to be the key to working with complex numbers. So as long as you know those two rules, you should be good to go. And to put it in an example here, the square root of -5, I could separate that into saying the square root of 1 times 5, and then pulling out that -1, and this would also be called I times the square root of 5, and that would be my answer. Conversely, the square root of -5 squared, I could rewrite as I square root of 5 squared, square both of those terms. As I see here, I squared is -1, so I would finally be left with my answer being -5. So let's start out here just simplifying using I. So we're going to simplify a radical, and then we're going to build up to doing like adding, subtracting, and then finally dividing. Here I want to simplify the radical, so the square root of -18. So I'm also going to work with just simplifying that number in general while also working with that negative as well. So what I'm going to do first is pull out that -1, so I could rewrite this as -1 times 18 all over the square root. And now what I'm also going to ask myself is, okay, can I break down that 18 anymore? And I'm going to rewrite this as -1 times 9 times 2. And why I separated this as 9 and 2 is because I want to ask myself when working with simplifying a square root, what's the biggest perfect square that I could pull out of 18? And that I could see would be 9, because 9 is a perfect square. I've seen in the past students try to like separate by just doing factors, so I've seen people try to separate 18 as 6 and 3. Here you would hit a dead end because neither 6 or 3 is a perfect square. So remember, when you're simplifying a radical, you're thinking about, okay, what are perfect squares I could pull out? If I was taking the cube root, what are perfect cubes that I could pull out? We'll deal with that next semester. So from here, I could pull out that -1 and call that I times 9, square root of 9 times 2. And similarly, I'm going to pull out that 9. The square root of 9 is 3, so that's what's going to happen when I pull that out. So my final answer would be 3i times the square root of 2. So just in general terms, an imaginary number is of the form a plus bi. Separating that out, a is the real part of that number and bi is the imaginary part. And looking at this as a chart, this might be helpful. We're not going to super get into this. And a real number won't have that imaginary part with it. A general imaginary number will have both parts, and a pure imaginary number will just kind of have that bi part. So finally, let's just work with basic operations with complex numbers. Here, I want to find the difference of 5 minus 3i minus parentheses -2 plus 4i. I'm going to treat this I almost like I would a variable, where I'd be combining like terms and just kind of moving forward like that. So what I'm going to do here is distribute that -1. I'm left with 5 minus 3i plus 2 minus 4i. And all I'm going to do here is combine like terms. So that 5 and 2 will combine to be 7. -3i minus 4i will leave me with minus 7i. So my final answer here in a plus bi form is 7 minus 7i. Now let's work with multiplying complex numbers. Find the product of 3i times negative 5 plus 2i. What I'm going to do here is I'm just going to distribute. And now I have negative 15i plus 6i squared. And notice here when I get an I squared is equal to negative 1. So that's how I'm going to rewrite it. And now 6 times negative 1 will leave me with minus 6. I'm going to rearrange this so it's an a plus bi form. My final answer is negative 6 minus 15i. Let's look at another example. Here I have 4 plus 3i times negative 1 minus 2i. Here I have two binomials, so I'm going to have to FOIL here. Here I have the first terms, negative 4, times the outside terms will leave me with minus 8i, inside terms minus 3i, and my last terms minus 6i squared. Here I combine like terms. Those middle terms can combine to give me negative 11i. That I squared will change to a negative 1, which will give me positive 6 overall. Finally, I'm going to combine those two real numbers, and my final answer would be 2 minus 11i. Finally, let's look at one more example, and you're going to notice something weird happen here. I'm going to FOIL, so I get 36 plus 6i minus 6i minus I squared. The middle terms will cancel out because it's 6i minus 6i. Those I squared will turn into negative 1. So I have 36 plus 1, which gives me 37. So notice here I multiplied those two complex numbers together and I got a real number. And in this specific situation, number pairs that are of the form a plus bi and a minus bi are called complex conjugates. And those are important because the product of a complex conjugate will be a real number. This will be important in the final thing that we're going to do today, which is dividing complex numbers. So when I divide complex numbers, basically the name of the game here is that for it to be simplified, I don't want a net or a complex number in the denominator. So how I could make that complex number into a real number is by multiplying the top and bottom by the complex conjugate of the denominator. So the complex conjugate of 3i would be negative 3i. So that's what I'm going to multiply the top and bottom by. When I do that, I'm going to be left with negative 27i minus 36i all over negative 9i squared. Simplifying this down, I see those I squareds. I change them to negative 1. Now I can see on the denominator, I'm left with a real number 9, and on the top, I turn that to positive 36. Finally, to simplify this, I'm going to just divide both parts by 9 on the denominator. I'm left with that. And finally, I'm going to reverse this just so that it's an a plus bi form. So my final answer here would be 4 minus 3i simplified. One more example, and that'll be it for today. I have 2 plus 3i over 1 minus 4i. So again, I'm going to multiply the top and bottom by the complex conjugate of the denominator. The complex conjugate here would be 1 plus 4i. When I do this, I have to FOIL on top, which will be kind of a long process, but the more times you do it, the easier it'll get. Here I should get 2 plus 8i plus 3i plus 12i squared all over 1 plus 4i minus 16i squared. Now from here, a lot of stuff's going to simplify down, so this won't look as ugly in the end. Those two middle terms will cancel out. These two middle terms will combine to give me 11i. Now I'm going to deal with the I squareds, turn those to negative 1. Simplify this down some more. I get negative 10 plus 11i over 17, so I'm good to go. That bottom is a real number, so I'm simplifying this correctly. And then finally, just to get this into proper a plus bi form, I'll separate out that 17. So my final answer, I have like the real part and the imaginary part fully separated. I'm going to leave this as negative 10 over 17 plus 11 over 17i.